Chapter 13, Lesson 13.1, Experimental and Theoretical Probability. Today we're going to learn how to describe events as a subset of a sample space using characteristics of outcomes such as unions, intersections, or complements. Our essential understanding is that probability is a measure of the likelihood that an event will occur. Let's try an example. You find an old clock in your attic. The hour hand of the clock is broken off. Between noon and 2, how many positions are possible for the hour hand? For a 12-hour period, how many positions are possible for the hour hand? And what is the probability that the clock stopped sometime between noon and 2? So let's analyze these questions. How many positions are there between 2 and 12? Well, we could be here, we could be here, or we could be here. So there are 3 positions. How many positions are in the 12-hour period? Well, there's 3, 4, 5, 6. I think we could have 12 possible positions. So the probability would be 3 divided by 12 for 1/4. So what we just figured out is the total of favorable outcomes divided by the total. And here is our formula. So here are the standards for today. We're going to be looking at sample spaces, complements, unions, intersections, independent probability, and we're just again trying to understand that probability is a measure of the likelihood that an event will occur. So probability of an event is the number of favorable outcomes divided by the total possible outcomes. Probability can be written as a ratio, a decimal, or a percent. A probability of 0 means an event will never happen. A probability of 1 means that event will happen. The closer the probability is to 1, the more likely it will occur. Probability can be written as a ratio, decimal, or percent. Experimental probability is probability based on an actual result in data. What did happen? So we have outcomes. These are the possible results of a situation or experiment. An event is a single outcome or group of outcomes, and the sample space is the set of all outcomes. And the probability is the number of times an event occurs divided by the number of times the experiment is done. So let me explain a sample space. A sample space are the things that could happen if we did the experiment. So if I flipped a coin, my sample space would either be getting heads or getting tails. Spinning the spinner, my sample space would be red, green, yellow, and blue. To roll this dice, my options would be getting a 1, a 2, a 3, a 4, a 5, or a 6. So sample spaces are the things that could happen. Let's try an example of regular probability, or experimental probability. A quality control inspector samples 500 LCD monitors and finds defects in 3 of them. What is the experimental probability that a monitor selected will have a defect? So we are talking favorable outcomes divided by total. So in this case, a favorable outcome is having a defect. So I have 3 defective TVs and 500 LCD monitors. So here is our experimental probability. You could leave it as a fraction, a decimal, or a percent. If the company manufactures 15,240 monitors in 1 month, how likely are they to be defective? So we know that our ratio is 3 to 500. If that ratio continues, we want to know how many out of 15,240 are going to have defects. So what I can do is cross multiply, and on my calculator I get 91.44. To answer this question, I would say approximately 91 TVs would have a defect. So based on the experiment that we did, we tested 500 monitors, and we found 3 defects. Using that experimental probability, we can make predictions for what would happen in future months. And this would affect our quality control, budget, and hiring numbers. Let's try another experimental probability example. While you're visiting a park, you choose 40 trees at random and determine that 25 are maple. What is the experimental probability that a tree chosen at random is a maple tree? So favorable divided by total. So a favorable outcome would be being a maple tree. So we have 25 maple trees, and we have 40 trees in our sample. That fraction reduces to 5/8. As a decimal, that's 0.625. As a percent, this is 62.5%. Any of these answers would be acceptable. If the park has 538 trees, about how many trees in the park are likely to be maple? So now, using our experimental probability, we want to make a prediction for the future. We could do a proportion like we did in the last example. We have 5/8 the trees are maple, so how many out of 538 are maple? Or we can think of this as a scale factor. We're starting with 538 trees. We know that 5/8 of them are maple, so if I multiply that out, that would give me 336 trees that we think would be maple. Theoretical probability. This describes the likelihood of an event based on mathematical reasoning. What should happen? What is the theoretical probability of rolling an even number on a six-sided die? Well, let's look at our sample space first. So the things that could happen on a die would be getting a 1, a 2, a 3, a 4, a 5, or a 6. So we want the theoretical probability of getting an even number. So an even number would be a 2, a 4, or a 6. So we have 3 favorable outcomes divided by 6 total, so half of the time we would get an even number. The complement of getting an even number would be getting a number that is not even, or in this case it would be odd. So the complement of getting an even number would be getting an odd number. What would be the probability of getting an odd number? Well, we also have 3 odds, which gives us a half. So if I find the probability of getting an odd number, I notice that getting an even plus getting an odd would equal 1. Those two events would be called complements. So here are some more examples. It being sunny out or it being not sunny, pulling a red marble or pulling a not red marble, the probability a person is happy or not happy. So if you add those probabilities together, those would equal a probability of 1. Let's try another example. What is the theoretical probability of spinning a 4 on the game of life? Well, our sample space looking at the spinner that's given would be a 1 through a 10. So we want theoretical probability of getting a 4. Well, there's only one way to get a 4. So that's 1 out of 10, which is 0.1 or 10%. If you roll the die 100 times and you rolled an even number 40 times, do you think the die was fair? So favorable outcomes was 40, total outcomes was 100, so that gives me 4 out of 10, or 2/5, which is 40%, which we can see from that first number. In theory, we should be getting half, or 50%, because either you roll an even number or a not even number. So do you think that these numbers are close enough for us to rationalize that the dice was fair? I would say yes. When you're doing an experiment, your results may be a little bit off of what should happen in theory. As long as our answer wasn't 10 or 15%, then I would think that things would be a little fishy, but because we're so close to 50%, I think our dice would be fair. If you roll a die 50 times and rolled an even number 32 times, what is the experimental probability of rolling an even number based on your results? So this is just straight up experimental probability. favorable outcomes would be 32 evens, total outcomes would be 50. If we turn this into a percent, we get about 64% of the time getting even. So this time we did a smaller experiment, where up here we did a larger experiment. So in our smaller experiment, we were higher than the 50%. So I would still say that our results would show that we have a fair die, and I think if we would do even a higher number of times, our results would get closer to 50%. What is the probability of rolling a sum of 7 when rolling a pair of dice? This table helps us see all of our possible outcomes when rolling 2 die. Up here, this is us looking at the red die, and down here, this is the blue die. So our 2 dice, one is red and one is blue. So one option would be to get a red 1, a blue 1, a 2, and a 1, a red 3, and a blue 1, and so on. So this is color-coded. We're going to look through our table, and it looks like we have 36 options. Inside the orange box shows us our options, so we have a 6 by 6 table set up, so that means our total number of options would be 36. So we want to figure out how many include a sum of 7, and these are the ones that are circled. 6 plus 1, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, and 6 plus 1. So the first 3 show a smaller red number, and the last 3 show a larger red number. So that it's kind of like they're just opposites of each other. A red 3, a blue 4, a red 4, a blue 3. So we have a total of 7, or excuse me, 6 if you count. So 6 out of 36, we always reduce our fractions, we get 1/6. And that is 0.16 repeating, so I'll round that to 0.167, or approximately 17%. The second question says, what is the probability of rolling a sum of 10 or greater? So now we have to think if we go greater than 10. So 6 plus 3 is 9, 6 plus 4 is 10, 5 plus 5 is 10, 6 plus 4 is 10. And then these two would give me 11, and then here's our only option that gives us 12. So if we're looking at favorable outcomes, we have a total of 6 of them, divided by 36. So again, we end up with the same answer as we did up there. So getting a sum of 10 and getting a sum of 7 turns out to be the same probability. Here's a jar example. A jar contains 10 red, 8 greens, 5 blue, and 6 white marbles. What is the probability of randomly selecting a marble that is not green? So I'm going to write this out as the probability of getting a not green. So that squiggle means not. So let's figure out our total. 10 plus 8 plus 5 plus 6 gives me 29. So our favorable outcomes would be how many are not green divided by our total. So we need to count how many are not green. So I would consider red to be not green, blue to be not green, and white to be not green. So how many total marbles are not green? 21. And how many total are there? 29. And this gives us about 72%. Another way to do that problem would be to work with its complement. What is the complement of not green? Green. So the probability of getting green would be 8 out of 29. So if we just focus on our fractions, 8 out of 29 is green, what fraction would be not green? 21 out of 29. Because you can see if you add these two together, you would get 29 out of 29, which is equivalent to 1 or 100%. You can decide what's easier, doing what they're asking you to, or finding the complement and subtracting from 1. This next problem is, what is the probability of getting a not red? So how many reds are there? There are 10 out of 29. So the complement of that The complement of not red was red, so that's where we get the 10 out of 29. So we're trying to figure out how many are not red. So if I subtract this from 29, it looks like there are 19 that are not red. And that works out to be about 65.5%. So either fraction, decimal, or percent for our answer. Here's our exit ticket. Please pause the video and see what you know. So on our spinner, our possible outcomes are 1, 2, 3, 4, 5, 6, 7, and 8. Evens are 2, 4, 6, and 8, so that's 4 out of 8, which is a half. Greater than 5 would be a 6, 7, and 8, which is a 3 out of 8. A prime is 1, 2, 3, 5, and 7, which is 5 out of 8. Not a 3, 4, and a 5 would be 5 out of 8. This concludes my video.